All right, now we are discussing the paper that came out now about 1.5 years ago, entitled Quantum Assisted Quantum Compiling, or QAC, QAQC, um, by a bunch of people at Los Alamos National Laboratory and Caltech, Louisiana State, and Michigan State. And so this paper basically addresses the challenge of compiling quantum algorithms, which is basically, right, you have some, whenever we're talking about all these algorithms, right, you have your nice little state, and you do your cool little gates. You got your entangling gates. You can do all sorts of these, whatever gates you would want. On your qubits, right, on your simulator or on your circuit designing task. But then every system, right, IBM, Google, IonQ, Rigetti, etc., has their own subset of supported native gates. So, for example, in the case of the IBM computer, I believe they do superconducting qubits. I'm not 100% sure about that. I'm not really a hardware knowledgeable person. The 5-qubit system, IBM QX4, has the gates Rx pi over oh my god, pi over 2, RZ of any arbitrary theta, and C naught. And so you have to convert, right? Well, you got a Hadamard gate. That's not one of this acceptable gates. And so the challenge of quantum compiling, also called quantum transpiling sometimes, is to convert your algorithm or your unitary, right? Because when you do all of these things together, right, like a simulator would, you could just multiply these all together, and that just equals some unitary matrix. So you want to convert this unitary, or decompose it, into a set of implemented gates on the hardware. And so that's a challenge, right? Because there are algorithms to do this, but it's often hard because you want precision, right? You want to be very close to what your target unitary is, but it's also challenging because you don't want it to be super deep, right? You don't want to have to use 50 gates to represent just this subset right here. That would not be efficient and would result in a ton of error, especially on near-term devices. So the work here proposes to use basically to sort of, rather than think of it outside of the quantum computer, right? Rather than be like, okay, I got this unitary I want to decompose. Let's do this mathematical steps on it. Rather than thinking outside of it, we do it on a quantum computer, or in this case, a simulator. And so we'll get into exactly what that looks like. I'm now going to switch over to the paper, which is publicly available. I downloaded it from arXiv, or the journal website, which is open source. So not breaking any laws by sharing this. So you can see here is the paper right here. And once again, we have the introduction, yada, yada, yada. We get all that. They also spend a lot of time detailing like the complexity of this, but once again, I'm not too concerned about complexity. I just want to do it, right? Let me actually turn on this so I can do this. There we go. So this is sort of a key section, right? This is the key idea, right? We have these continuous and discrete variables that we're trying to optimize. And so this is sort of the general framework that they propose. So you optimize the for a given discrete set, right? For your given gate set, you optimize the continuous variables, then you try another gate set, and then you optimize the continuous variables with that. And if that gate set performs better, then you can accept that. And so that's sort of the optimization loop, is a hybrid sort of, you optimize the continuous parameters, and then you can optimize the structure parameters. And so they introduce a number of cost functions. The only one that I'm going to actually implement in code is this Hilbert Schmidt test one, which I don't do it the same way they do it. But basically what this is, right? Okay, what is the trace, right, between these two matrices is going to be, well, right, this is sort of like, if this is the inner product, right, this is sort of like the, I don't want to say distance, but like if you consider that this is the square of the inner product, that's kind of like the distance, right? If you consider the square of the inner product of like some Euclidean distance, that's sort of an idea, right? That's not the exact same thing, but that's the idea, right? That's the distance between them. So if the distance is going to be 1, which is ideal, right? Because if we consider like a vector, right, just a standard x dimensional vector, and we do the inner product, right, and these are vectors instead of, maybe I'll just call them x and y, right? If they're orthogonal, right, if they're, so that means they intersect, right, at a right angle in all dimensions, then this is going to equal, actually not, this equals 0, right? The dot product or inner product of orthogonal vectors is 0. So that means they're far apart intuitively, right? They're not near each other. They're sort of as far apart as could be, right? Because if you consider a two-dimensional vector orthogonal, even if you go more this way, then you're just bringing it closer on this side. And so that's sort of the intuition behind what's going on here, is that they're measuring the distance, right? And if this is 1, then they're the same. And if it's 0, then they're different. And intuitively, you can also see, yeah, this is what they say here, right? This is just the fidelity. So if you're familiar with quantum state operations, this is the same as the fidelity, which is simply, right, the square of the inner product. That's all it is. And so this trace operation, right, we can also write this as, this is commonly how you'll see it in Dirac notation, right? This is the same thing. These are all just notational differences. So 1 minus the fidelity is the cost function. And so they introduced other cost functions that might or might not be necessary as the size of the system grows. I'm not going to look at that. You can just see they introduce a local Hilbert-Schmidt test, which is unimportant here. And so what is this Hilbert-Schmidt test? It's a way of evaluating. This is what it is, right? So if we have our little our target unitary right here that we're trying to evaluate, and this is our estimation, or I should say learned, then we want to evaluate what this is on a quantum computer, right? Because the whole goal with this is to evaluate on like on hardware, right, would be the goal here. And so we can say, we can do these Hadamard gates, C naughts from each one of them, and then do the operations and then undo it. And so intuitively, right, if these are the same operations, then of course this will all be zeros, right? Because you just undid everything, right? These are the same. And so when you when you did this operation, it just reversed it, right? This just undid this. And so intuitively, right, if they're the same, this is going to be all 0. So we can see the probability that the qubits are all in the 0 state is equal to the fidelity. And so, yeah, you can see that it computes the magnitude of this inner product. And so, obviously, if they're the same, then this is going to be 1, so our cost function will be 0. So that's the idea of implementing on hardware. We don't really concern ourselves with this because I'm just doing this on simulator, so we have access, right? We can just compute the fidelity using knowledge that we wouldn't otherwise have. So this is the section where they spend on talking about the complexity, which doesn't really matter to me, to be honest, right? And complexity either works or it doesn't. But we'll continue on. So now this is what section 6 and 7 is what we've implemented in code. So first we have this single qubit gates. And so these are the two that I'm going to focus on. So we have to optimize the gate set, these gates right here, right, as presented before, for the to represent these X gates and H gates. So how do we do this? That's where I'm going to actually jump down now and talk about the optimization loop. So if I scroll all the way down here, and this is what we have implemented, right, is this algorithm one right here. So basically what they do is they go through and for a given circuit structure, they use Bayesian, Gaussian processes, that's what GP means, to minimize, which is a gradient-free approach to minimization, to minimize the parameter, the continuous parameters, and then they vary the structure, right, and then either accept or don't accept the result, and so they repeat this process. And so that's what we have implemented. I change it a little, and I'll talk about that in a little bit, how I change it to get the exact same results. But going back up, the second thing we do is on section 7, we have this example, right, where we have a static circuit structure that we're learning from. So we just have to optimize the parameters, and we use a gradient-based approach for this one. And so we consider example 2. So basically we have a bunch of RZ gates followed by some entangling C0 gates followed by more RZ gates, and the trainable unitary has the same structure as this. So the same structure basically, and we're just trying to reconstruct these weights basically, and the weights are just random. And so one thing they mention, I don't know where it is right now, but as you increase in size, the likelihood that you're going to get pretty good fidelity just from like these random angles is somewhat high. And so that's sort of the motivation for the local fidelity test. But I just do a set of Hadamard gates before each of these, which sort of artificially creates more divergence, which can help it learn. So that's basically the idea. We'll get into this, and this is for example 2. And I should also note that they have a complex gradient-based optimization procedure for this here, which I do not follow, right? This is a lot of complex stuff, but why do that when you can just throw atom at it? That's the real, machine learning researcher approach right there. So yeah, we'll get right into the code then by just go over here, do that. Okay, so first we'll get into the single qubit example, and I'll show how it's different. So first we have our we import this GP minimize from the optimization library, and we have our target unitaries that we're learning, which are the X and the Hadamard gate, the H gate. So we can just create them pretty easily. And so our initial structure, right, is random. For these single qubit ones, we just initialize it randomly. And so there's three choices. Remember, there's the Rx, the RZ, and the C naught. However, because it's only one qubit, there's no point in having the C naught. And because I sort of allow for arbitrary depth or a defined depth, I also include the identity gate. And so, yeah, you just randomly initialize this structure. For the fidelity, remember, we can just simulate it. We can get the final state vector of our prediction. And remember, we do, so this is basically, right, I can't do this. This is the, so this is our predicted, right? This is what this is computing, right? Now this is the, this is this, right? This is what's going on right here. And so that's computing the fidelity. And so, yeah, that's pretty straightforward. And for the targets, right, because we don't want to simulate them every time, that'd be a waste, we pre-compute their state vectors. And so with that, we can now write the optimization loops, and you can see they're slightly different because in order to adjust for the length, right, because you can get the same result by doing sort of redundant operations, but we sort of want to penalize that, right? We want them to be as short as possible in terms of non-identity gate operations. So I penalize the number of, or I guess I should say I reward the number of identity gates, which is a slight change. And so for 10 iterations, we go through, we create the initial random structure, we minimize any continuous parameters, and if it's better than what we currently have, we keep track of it. We do this for both X and H, and we just repeat this process, right? We just go through and we optimize any continuous parameters. Note that it's possible that there are no continuous parameters, and then we go through and we keep track of what is best. And so we can then get the results. The graph isn't particularly meaningful. What is meaningful, and I'll show this in just a second. Here we go. So keep in mind, let me bring this back up. This is what we're going for, right? X is just 2 Rx rotations, and H is 2 RZs and 1 Rx is basically what we're going for. And so if I show you, I've already run this code, I don't want to rerun it. This is what the optimization routine looks like. And ignoring all of this, right, you can see I ran the code right here. This is just printing at every loop. You can see at the end here, this is what it outputs. So this is the gate, the cost function, the circuit, and the parameters. So you can see this is Rx. This is slightly different, right, because originally it's RZ, Rx, RZ, but it's the same. It's the same thing. So we have Rx and then RZ of pi over 2, and then Rx for our Hadamard gate, so 3 qubits, or sorry, 3 depth. And then for our X gate, we do learn the Rx and Rx. And so that's the idea behind the single qubit operations. Now we will talk about the comparison of example 2. So we create our target unitary, which is this randomly initialized RZ followed by entangling followed by RZ. And note that it's also a initialized with Hadamard gates, and our circuit structure that we're trying to learn has the exact same structure and gate setup as our target. And also notice that this time we just have the parameters, which is 2 times the number of qubits because we have 2 layers of RZs. So now for iterating from 1 to 20 qubits, we can simulate this. We take the we can take the hold on just a sec. All right, sorry, I was just thinking about something that I'll discuss in a second. But we can initialize the qubits, create the target and the learnable circuit, and we initialize the parameters. And now this is where I want to note something. We just use Atom, right, instead of their complex optimization routine. But also in this initialization, this probably won't matter, and this might be changed a little bit. Previously, the gradient of the fidelity operation returned a complex number and had type complex 64. But I recently saw, just like today, like a few hours ago, that there was a merge in the TensorFlow quantum that made the gradients be of type float 32, I'm pretty sure, and not be complex. So this might not work if you just installed the latest nightly version or whatever of TensorFlow quantum. So keep that in mind. Just change that to float 32 if you're getting some like complex is not allowed error. So then we have our target, right, which is just this circuit up here. We have our guess, which is just this randomly initialized circuit. And for 80 iterations, we optimize this. We use gradient tape. So we have our values, which is, so the way fidelity works is we have our parametrized circuit, the parameters and the parameter values, and the target circuit that we want to compute the fidelity with. As far as I know, I don't think the target circuit can be parametrized, but I could be wrong. I've just looked into this because this is new with the TensorFlow Quantum 0.5 release. And so because this isn't like, there's no model here, right? We're not using any layers. We have to actually specify what we're gonna like care about, right? It doesn't know, because normally if you feed a model, right, if you do some forward operation on a model, it'll be like, oh, I know that's what you're gonna want gradients from, but it doesn't know. These are just arbitrary operations, right, that we're doing. So it doesn't know what to care about. And so that's what this tape.watch is telling it, saying, hey, keep track of this information. Watch what happens to these parameters so you can calculate the gradient. So we compute the fidelity. We get the cost as the 1 minus fidelity. We calculate the gradient with respect to the cost for these parameters, and then we apply the grades. And this is where I was just thinking, I realized I don't actually know what the default, right? Normally you have the default differentiator for layers, right? It's either adjoint or forward difference. I don't remember what it's set to right now. But this has no layers, so I don't know what the default differentiator even is. Maybe, hold on, let me check if I just see real quick if it says in the docs, right? Because it's something that is differentiating this circuit somehow, right? Because it's calculating the gradients through it. Let me just go to the math operation and see if the gradient yeah, I don't know. I honestly don't know. I'm gonna ask the the team maybe how that's done. Maybe it's from the if I look at how the inner product is calculated, maybe I'll see. Let's see, grad zeros like inner product grad. Okay, let me just spend 1 second. Okay, yeah, I didn't figure it out. It's possible that it's parameter shift, and it's possible that, but I would guess it's more likely that it's adjoint or some sort of back propagation method. But I will probably ask about that. So that's what we're doing, right? We're just computing the loss as the n1 minus fidelity and updating the gradient and keeping track of each of these. So if we plot this, I will open this up. You can see that as the number of qubits increases, the difficulty sort of increases. It takes longer to converge. And so this is sort of similar to the figure I showed from example 2 in the paper. However, they said that at larger intervals or at larger qubits, it was the full fidelity cost function was inoperable, and that's probably true, right? Using their optimization technique and their circuit structure, because remember I added Hadamard's to make the optimization easier. But it's just something to consider that with this you can see how this is doable. And so yeah, that's basically it for this discussion. And I know I titled this, replication of some paper. I should probably stop doing that because this really isn't a replication. This is really more of a analysis or inspired by code. I don't know what to call it, but I guess for now I'll keep calling it replication. But yeah, that's the 2019 paper, Quantum Assisted Quantum Compiling.